All right, welcome back. We're going to finish up section 2.2 here with another day of alternative forms of derivative. We're talking about the alternative forms of derivative. We've got the alternative form that allows us to find the derivative at a point, but we also want to be able to look at an alternative form of the definition of derivative. So let's go ahead and talk about the definition of derivative for a second. We have the limit as h goes to 0 of f of x plus h minus f of x, and that's all divided by h. And some things that are kind of arbitrary here is this h value. What does that h talk about? If we go back to the graph of a function, we had our x value here. We made our point. We came over some h value, and we got another point of x plus h. And we came up to this point, and that gave us f of x plus h. Over here, this was f of x. So this h value, this change in x, can be very arbitrary. That h could be delta x, which we've seen quite extensively this year. We can also make it, an a. A goes to 0. We can make a b go to 0. We can make it whatever we want. We normally see it as delta x or h, but we could see it at anything you want. You could put theta goes to 0 if you want. So what we're going to see is that this h value here could be any one of these notations as long as this is going to 0. And then that's going to change this number down here. What we want to see, though, is that this f of x is normally always going to be what the function is. How else could we define this, though? What happens if this were to be switched around? So what happens if we started with f of x and subtracted off f of x plus h? What would that look like? So we would see the limit as h goes to 0 of f of x minus f of x plus h. And we would divide it by the x minus x plus h. Simplifying that, we're looking at the limit as h goes to 0 of f of x minus f of x plus h over, the x's here would cancel over negative h. So we should see that these two are identical. They're going to give us the same value when we take the limit as h goes to 0. But notice here the numerator gets flipped and then the h becomes negative on the bottom. That should hopefully be intuitive, since if we pull out a negative or we factor out a negative out of the top here, that negative could slide down to the bottom with our fraction rules. So that could be another form that we could see it. Well, what happens if we take this graph and we could do some other things with it? Remember, we're always looking for a secant line to become the tangent line. So I'm going to draw out a nice graph here. What happens if our x was here? So that's our f of x. And I brought over an h value. So we get x plus h. And here we have f of x plus h. But over here, we took an h value as well. That would be the same distance, wouldn't it? And I came up here. This would be f of x minus h. Notice we're now going in the negative direction, so we're subtracting that value off. So this would be the same distance here. I could find the slope of the secant line between these 2 points. So I could take the limit as h goes to 0. Again, that h is talking about the distance here. No, this was x minus h, wasn't it? So we're looking at f of x minus h minus f of x over x minus h minus x. Cleaning up this, we're looking at the limit as h goes to 0 of f of x minus h minus f of x all over a negative h. So that's slightly different than what we saw up in these forms. But again, we should notice some similarities. Our variable is still going to 0. We're still taking f of some x and doing something with it, some form of moving it left or right, still subtracting off the original function and dividing it by an h. We could, also with this, we could take our secant line to go from f of x plus h to f of x minus h. So if I go through here, then that limit would be h still going to 0, that distance, but we would take f of maybe f of x plus h minus f of x minus h, that would be my two y values, divided by x plus h minus x minus h. Cleaning up my denominator, I'm going to take the limit as h goes to 0 of f of x plus h minus f of x minus h, dividing it, multiply my negative through, my x's will cancel this time, and I have h plus h, which gives us 2h. So all of these forms are things that we could, I know it's mind-blowing, but we could represent the derivative or the slope of the tangent line. Why do we do this? Well, because on the AP exam, we're going to give you, where do my problems go? Oh, there they are on the back. We're going to give you some problems that are going to ask you to recognize what this limit is and be able to find the derivative. And if you can do it, it becomes very quick and easy, and you get the answer in a timely manner. If you don't, your life becomes a little more complicated, and we'll look at both of those ways here in a second. So some things to look for. One, we want that limit to go to 0. We want to take the limit, or the limit is going to be taken by the difference of two quantities. So we're going to be subtracting two things. Remember, we had that f of x plus h minus f of x, or f of x minus h minus f of x plus h. So we're always subtracting in the numerator there for this example. Was there a value that was plugged in? So are all the x's gone? Can we identify the function? If we can identify the function, we can take the derivative, then we can plug in the value if we need to, and we've got our answer. So let's go ahead and look at an example of where we might see, or what we might see this as. We're looking at the limit as h goes to 0 of 2 times x plus h squared minus 2x squared all over h. So if, again, remember that definition of derivative, f of x plus h minus f of x divided by h as h goes to 0. So this is a very classic example. Notice here we plugged our x plus h in. If I were to pull that x plus h out and just put x's in, I would have my function, my 2x squared. Minus f of x, here is my function. This is the important piece right there. I know that my f of x is 2x squared. What does this ask us to do? It's asking us to take the derivative. Find the derivative, find the instantaneous rate of change, find the slope of the tangent line of this function, 2x squared. Well, we know the derivative of 2x is going to be 4x. And we're done. We now know that the slope of this was just taking the slope of, or finding the derivative of this function, which is going to be 4x. And we got it. If we look down here at example 2, looks like there's a typo. That's not good, is it? That should be a 3, it looks like. All right, so what do we have here? We have 3 times an x plus delta x minus 4 times x plus delta x. Delta x is going to 0, so that should ring a bell to us. Hey, definition of derivative, because we're looking at f of x plus delta x minus f of x all over our delta x. That kind of looks like f of x plus delta x is here. Looks like our f of x is maybe here. They've distributed the negative already, so our original function, it looks like f of x is 3x squared minus 4x. Our derivative, that's what it's actually asking for, is 6x minus 4. Now, could you go ahead and multiply this out and clean it up? Absolutely you could. I guess I could have showed that up there as well. So if I multiply this out, I would have 3x squared plus 6x delta x plus 3 delta x squareds minus 4x minus 4 delta x. I'm going to run out of room, but I'm going to be good, plus our 4x. So if I cancel out my 3x squareds, cancel out my 4x's, factor out my delta x, as we've done in the past, we get 6x plus 3 delta x minus 4 over delta x. And we're taking the limit as delta x goes to 0. Delta x's cancel. This delta x goes to 0. We take the limit, and we end up with 6x minus 4. Which one would you rather do? multiply it out to get 6x minus 4, and we know that that's the derivative. Or recognize that our function was 3x squared minus 4x, and we're looking for the derivative, which gives us 6x minus 4. Time consuming here, we can work out the problem there pretty easily and pretty quickly. Here we're looking at the limit as h goes to 0 of 5 times the quantity x plus h minus 5 times the quantity of x minus h squared all over 2h. So that's going to be, again, our derivative that we're looking for, and it's an alternative form. If you recall, we could have had that f of x plus h minus f of x minus h all over 2h. That's where we're taking the secant line between 2 points. So maybe here's our point. Our original point was here. We had our x minus h and our x plus h there. So if we go ahead and look at this, we know that our function, f of x, is going to be 5x squared. Our derivative, f prime of x, is 10x. Again, if you don't like that, you could go ahead and multiply that out. I don't know who would want to multiply it out, though, but you can. In the next example, we have delta x going to 0 of 5 minus 3 times 1 plus delta x, and then minus 2 all over delta x. I think this was one of our assignment problems a while ago. Notice here we don't have any x's, but if I think about my definition, I had f of x plus delta x, f of x plus h, or delta x in this case, delta x's, minus f of x over delta x. So I got that delta x. Looks like all of this is being put together as my f of x plus delta x. So then it looks like my function is going to be 5 minus 3x. And in this case, since they've gotten rid of the x's, they put they put 1 in for x. They're asking us for f prime of 1. So to find f prime of 1, we first find f prime of x, which gives us negative 3. So f prime of 1 gives us negative 3. And that gives us our answer. Excuse me. All right, just a couple more examples, and then we'll wrap it up here. Again, just looking at some variations of this. Here, we're taking that a. No, we don't have a. We didn't have an a before. We had h. We could change those a's to h's. We could change the delta x's. Doesn't really matter. But this is asking us to find f prime of, and here they're replacing the x with negative 2. So we're going to find f prime of negative 2. When I first find my f of x, it looks like my f of x. So if I take my x plus a out and just put my x in, I'm looking at x to the third. My derivative, f prime of x, is 3x squared. So f prime of negative 2 gives me 12. And that gives me my answer. And last but not least, we have this function. This one, we're switched backwards. So our f of x is going to be x minus 5. I don't need the parentheses there, do I? So my derivative, f prime of x, is going to be 1. So again, things to look for is the limit going to 0, which all of these were. Are we taking the limit between two differences of two quantities, or differences between quantities? Was there a value plugged in, or is it just in terms of x's? Then we identify the function, take that derivative, and if it's asking for the value at a point, go ahead and plug that point back in. Good luck!